We have two more features of the graph that we can determine using these moving frame vectors. One of them is the curvature, and that basically tells us how curvy is the graph. So like circles, very curvy, lines, not very curvy. This will be kind of measured by the rate of change of the tangent vector over the speed of the graph. That's kind of what that's going to be. And then the torsion kind of represents how planar is the curve at a certain point. Is it well represented by a plane, or does it twist out of the plane a whole bunch? That'll make a little bit more sense once we kind of have the visual of the oscillating plane, but we don't have that yet. But that is going to be the value of tau such that the derivative of the binormal vector divided by the speed is negative tau times the normal vector. Does such a thing exist? You bet it does. So let's go ahead and try to calculate these using what we found already. Now, to find kappa, we just need to, or to find the curvature, we just need to take the derivative of our unit tangent vector, which we've kind of already done. In fact, if we scroll up, we'll see that we already have that. So maybe we just won't go ahead and bother finding that. So let's look, see what we did. Oh, look, it's our previous work. We noticed that we had to find the norm of the derivative of the tangent vector when we were finding the principal normal vector. And we did that work. It was a really fun time. And what we ended up finding was that it was 3/5. So we can go back down here and say, hey, this is going to be 3/5 from previous work over, and then what's our speed? Our speed is just 5. So this is going to be 3/5 times 1/5. It's 3/25. So in this case, the curvature generally speaking is a function of t, but in this case it's a constant, so that's nice. So we kind of, that isn't terribly surprising that our helix has a constant curvature. Now we want to find the torsion. To find the torsion, we need to start by finding the derivative of b divided by the speed. And we can find that. So the derivative of b is going to be positive 4/5 cosine of t, positive 4/5 sine of t, 0. And remember, we need to divide this by the speed. Fun fact, I'm redoing this video because I forgot to do that. So make sure you don't forget to do that. So we divide by that, and when we do that, we're going to end up with the quantity 4/25. It's a 4, not a 9. 4/25 cosine of t, 4/25 sine of t, 0. And now what we want to find is there some scalar so that b prime of t over the speed equals negative tau times n of t. In other words, we want to find a scalar so that 4/25 cosine of t, 4/25 sine of t, 0, equals negative tau times negative cosine of t, negative sine of t, 0. Now, in this case, you can probably tell what it is right away. You can tell that tau is going to be 4/25, but let's say it wasn't that easy to tell. What you can do is, this needs to be true for all components, so let's just go ahead and look at the first component. we're looking for a scalar such that 4/25 of cosine, 4/25 of cosine t equals negative tau times negative cosine of t. In other words, it equals positive tau of cosine of t. Go ahead and divide both sides by cosine, and we find that tau, our torsion, equals 4/25. So there we go. Again, that could also be a function of t, depending on how these moving frame vectors turn out, but in this case it ended up being constant. So we've practiced with a lot of formulas, and hopefully that gives you an idea, just a starting idea of what kinds of calculations you need to do to obtain these different quantities and these different formulas for these different features of a curve. So there you go.